Welcome back. Happy that you are here. We will now have a session with 5 presentations on different technologies, innovations, and use cases. And it will be 15-minute slot, roughly 10-minute presentation, and then a few minutes of Q&A. And please ask questions again in the Slido app. Vote for the ones that you like most, and we'll discuss them here on stage with the experts. The first expert is here, Dr. Marc Isabelle. He's the founder and director of European Economics, and he will talk about public funding, obviously a topic which has been discussed in the morning already and a lot, so very important. He regards this as the challenging venture of clean hydrogen projects in Europe. And Marc, we are very curious what you offer as potential solutions maybe to that challenge. So here you go.
Thank you very much. Good afternoon, everybody. I'm Marc Isabelle. I'm the founder and director of European Economics. We are a pure player consultancy on public funding. So what we do is support industrial companies to secure public funding for strategic projects, many very large projects. The key figures about our track record are on the slide for the general track records and for our track record also in the hydrogen economy. For hydrogen specifically, we supported 59 projects and we helped this project secure 11.6 billion euros. So what we do is help the companies to define public funding strategies for very large projects. We support the companies to prepare the applications for European calls or national calls. When it comes to state aid, meaning member states' money, like in the IPCEIs, we also support the companies to go through the European process about regulation for state aid, which is about competition matters. The company cannot receive the money from the member state before you receive the green stamp from the European Commission. So we prepare the files and we help the companies to answer the questions from the European Commission. And we also provide follow-up services once the project goes into execution. Well, apart from that, basically what we do when you jump into the, let's say, public funding jungle, we act as a compass because it's a jungle, but we do it every day with specialized consultancy. So we feel at home in that jungle. We help you find the right directions. We also act as an accelerator because we can help you implement public funding solutions in a very fast track, so to say, depending, of course, on the willingness of the member states and the European Commission to follow that support. When it comes to very large projects, we will help you also find different funding solutions to combine in order to be able for you to kickstart your project. So we act as the architect here. And sometimes the regulation about public funding, when it comes to state aid specifically, goes into very strange concepts, such as distortion of dynamic incentives and the like. So you will not understand the words most of the time. They come from economic theory. We are a team of economists, and we will act as a translator to support you to secure public funding. So my speech today will be about the difficult life you are going through of strategic projects in the hydrogen industry. And the first slide is to emphasize the importance of the hydrogen industry for Europe specifically. There have been a lot of crises, a lot of huge challenges coming from global warming, the dominance of China in commercial trade, the COVID crisis, the war in Ukraine, the American Inflation Reduction Act, and Europe has been reacting quite well to all the challenges, and the European hydrogen industry is a cornerstone in the European strategy to face all these challenges. And you see here the 4 IPCEIs that were supported in Europe to kickstart the European industry, and you see that the Innovation Fund is also part of the funding opportunities that you could look at, and more recently, the European Hydrogen Bank. So as you most probably know, there were 4 IPCEIs on hydrogen that were started. 3 have been validated by the European Commission. 1 is still under assessment. And the hope there, starting in 2019, I remember the first meeting in Brussels in October 2019, was that the IPCEIs could kickstart the European industry for hydrogen. There were more than 120 projects that were started in these IPCEIs, and they secured close to 30 billion euro grant which presumably could have solved the chicken and egg problem in the European hydrogen industry. But the issue is the following. This project was started in 2019, 2020, 2021. And when a given project asks for 100 million euro public funding, this is calculated based on the fact that these 100 million euro could help the company secure an internal rate of return for the project equal to the WACC. This calculation was made based on the economic conditions prevailing in 2020, 2021. The validation for this IPCEI came in 2022, and then everything changes. The prices of green electricity went up, the cost of capital went up, the labor cost went up, everything went up. And as you know better than I do, the price of hydrogen went up from 35 to 60%, which is something displayed on this slide. So basically the solution that you are facing now as the hydrogen industry is that the IPCEIs, high to X, meaning high to tech, high to use, high to infra, high to mobility, will not be able to kickstart the European clean hydrogen market. Specifically, when we look at the projects on the demand side, well, they were profitable with 100 million euro public funding, with a price of green hydrogen maybe around 4.5 euro per kilo at that time. But now this price cannot be met anymore. So the projects on the demand side are not profitable anymore with the funding that's secured in the IPCEI, and then you have the domino effect again. No demand means no supply, means no technologies for electrolyzers. This is maybe over-pessimistic, but we basically go back to the initial situation in 2019 with the chicken and egg problem, supply waiting for the demand and vice versa. So basically, the situation that we are facing now is the same that you faced some years ago. The expansion of the European clean hydrogen industry cannot be unlocked without additional public and free money. Debt doesn't make sense, equity doesn't make sense because the projects are not bankable, okay? So the only solution is to go back to the member states, the European Commission, to ask for more free money to be able to increase the profitability of these projects. And you have several quotes here on the screen that substantiate my statement here, from projects that say, okay, we hope we could do it, but now we can't do it anymore, given the new economic environment. So the solution is not on us, the solution is on the governments and the European Commission. So what's the conclusion? We must find a way out, we must act quickly. I think everybody understands that the timeline, there was a kind of hype at that time with the IPCEIs. The promises were very important, very strong, and we realized that it would be a bit more difficult than what we expected at that time. So member states and the European Commission must find a way to secure more free money for clean hydrogen projects. If we give a look at the European targets for 2030, you know the numbers very well probably. The EU calls for 100 gigawatt of green hydrogen capacity by 2030. From my understanding from the project that we supported, this requires more or less 100 billion euro of public funding for this capacity. For 7 years, that's more or less 40 billion euros per year. We are very far from the target. So the solution that we have today, that was started by the European Commission under the Innovation Fund umbrella in 2023, is the so-called European Hydrogen Bank. And they developed these auctions as a service. Basically, the projects bid on a green premium, the electrolyzers project, bid on the green premium. There was a budget of 800 million euros this year to finance the best scored project, meaning with the lowest bid in terms of green premium. But the projects that are not funded by the European Hydrogen Bank could be funded by the member states. This is very explicit in the documents for the European Hydrogen Bank. So if the member states have money to support electrolyzer capacity to produce green hydrogen, they could follow the bids that are not selected in the European Hydrogen Bank call to support themselves more projects to meet new investment capacity for electrolyzers. So I think basically we have a mechanism here I heard this morning that there were also auctions in France, auctions in Germany, auctions at European level. This is to support the production of green hydrogen, to meet also the price that the demand would be able to pay. I think I remember that the price of grey hydrogen is more or less 1.5 euro per kilo. If you subsidize the manufacturing of green hydrogen, you could be able to meet that target. And this is my conclusion. Thank you very much for listening.
Thank you very much, Marc. There's a question. Please stay on stage for answering this one. And it's the big question: why are you there in the world, basically? But maybe you can elaborate on that a bit. Why is there a need, provocatively said, for another costly advisor, when, for example, Hydrogen Europe has a great offering on R&D funding and other supports? So what is the sweet spot, basically, that you are filling with your company?
Yes, what was very important in the IPCI, just to reflect upon support for R&D, the new thing in the IPCI is that not only R&D could be supported, but also the so-called first industrial deployment of innovative solutions. For example, we supported several projects that would invest into the development of innovative electrolyzers. Okay, but the support from the governments under IPCI rules would not stop at the pilot scale, but the companies, conditioned of course on the success of the pilot, could invest into the manufacturing, the gigawatt manufacturing plant, and be supported for the ramp up of the gigafactory. So this is where there is a big difference between IPCIs and state aid for R&D. It goes to the first industrialization and the first commercialization of innovative products, and we supported a bunch of projects going through this scaling up phase, so to say.
Okay, good, thank you. Now, here comes a thesis. It would say that the only way to get hydrogen going, the hydrogen market going, will be to increase the cost of fossil fuels. So why not increasing the cost for emission certificates across all sectors, and then just have the market solution, basically, for the hydrogen market?
Well, my humble opinion as an economist is that if the solution was that simple, we'd have implemented the solution already. So it goes, from my opinion, in different directions. Of course, putting higher taxes on fossil fuels could be part of the solution, but you're just talking about fuels for cars, for example, you probably know that taxes represent already 80% of the price that you pay, more or less. So we already went very far in that direction. Public funding for hydrogen use was also part of the solution. Just to give one example, we supported a number of hydrogen solutions implementation in the steelmaking sector to move away from coal to the reduction of iron ore through hydrogen. This has huge cost, but I hope that at the end of the day, in 1 decade from now, most of the steel made in Europe will be decarbonized through public funding. Another way, of course, to have the hydrogen market more competitive is to scale up. Okay, you know what economies of scale are, for sure. So far, the green hydrogen market is very small, so we have no economies of scale. When the market will expand, of course, the cost will go down, and if the price of a carbonized solution goes up at the same time, at some point in time, it will become competitive, and public funding will not be needed anymore, for sure. So it's a combination of many mechanisms to be able to trigger clean hydrogen projects.
Maybe one last question. What is your, let's say, forecast now for the next years with regard to public funding? How will the whole scenery develop? Give us some insights.
Well, I cannot speak in place of the governments for sure, but you know that the solution, just looking at interest rates, was very good for the member states until 2022, before the war in Ukraine, before inflation. Germany, France, Italy could raise money at very low interest rates, so they could support new projects in the hydrogen industry at a very low cost. Now the situation is completely different because of inflation and increasing interest rates. The budgetary position of, let's say, very strong member states such as Germany is very different now. You know that Germany, it will be difficult for Germany to fund new projects in 2024 specifically. Yesterday, the French Ministry of Finance said more or less the same thing. So I think it's time also for the European Union and European Commission to leverage on its own capacity to fund new projects for some time until the member states can be safe again and go back to funding of new projects.
And is this also the solution for poorer member states? Because here the anonymous thinks that additional funding, free money might be available in richer EU countries, but what about poorer member states?
Yes, this is what state aid regulation is about. Of course, the idea is to keep a level playing field in the European Union, not to have the big member states being able to attract all innovative investments and large investments. And one solution for that was, for example, in COVID times, you have the so-called Recovery and Resilience Facility, which was European money delivered to the member states to implement innovative projects and infrastructure projects. And the member states that were most impacted by the COVID received a lot of money. This is the case for Spain, Italy, for Poland, for example. Or when you look also at the Just Transition Fund, this is a fund dedicated for the transition away from coal and fossil fuels. And here again, it's not the richer countries that receive the more money. So there are some mechanisms to kind of balance the budgetary positions of the various member states.
Good, Marc. Thank you very much for your contribution.
You're most welcome. Thank you.
And without further ado, I'd like to welcome to stage Dr. Wolfgang Schleifenbaum, the head of the production area hydrogen at Bosch Manufacturing Solutions. Welcome, Wolfgang. And you will talk about water purification as a key enabler for green hydrogen production. Looking forward to your presentation and the short discussion afterwards.
Thank you. Water and energy are two of our fundamental resources on the planet. Can we utilize the one without managing the other? In nature's water cycle, the sunshine evaporates water from the Earth's surface, turning it into clouds and storing the energy there, which is then released during condensation. We can look at this. Well, here are no windows, but in Berlin today it rains. When we move into the green energy transition, we again use sunshine, solar energy, and other renewables to split water molecules into hydrogen and oxygen, storing vast amounts of green energy there in those gases in order to release them in the processes that use the hydrogen. And we all want to achieve so much, these vast amounts of energy, but it must be clear that we need to provide the water to do so. Ladies and gentlemen, welcome to my talk on water purification technologies. The electrolysis projects that start throughout the world, they are in industrialized areas where we have tap water. They are in desert areas and offshore regions because the renewable energies are abundant there. And there you find saline water. All these regions have in common the ultra-pure water needed for an electrolyzer to process, it's just not there. So every electrolyzer that we set up will have as an accompanying partner a water purification device. And this device has to make sure that the water the electrolyzer processes is ultra pure in order not to jeopardize its lifetime and in order to keep a reasonable levelized cost of hydrogen. The purity is measured in electrical conductivity. Ultra pure means very low electrical conductivity. Depending on the electrolyzer technology you choose, it's 0.1 microsiemens per centimeter. And the water that you use, for example, saline water, has conductivities up to 50,000 microsiemens per centimeter. That means a lot to do for this water purifier. The amounts of water that are being used, you see on the slide, for a kilogram of hydrogen, we need 9 kilograms of water. Just to get you an idea, in this bottle is some water. We could turn this, after purification, into green hydrogen, and that would store about a kilowatt hour of energy. Now, you know, we're not talking kilowatt hours here. We're not talking gigawatt, we're talking terawatt hours, so we need vast amounts of energy. It sums up for the net zero scenario to about 4 cubic kilometers of water per year. That sounds a lot, and it is a lot. But again, if you look at the different industries using water, chemical industry, agriculture, the water needed for globally for green hydrogen production is just 1.8% of the water consumption of humanity today. So it's small. Nevertheless, the message must be, in those areas where we make the electrolysis, we still need the water. So if you go to a desert area and you have no water at all there, of course you have to make sure it's there. So water availability is a very important topic, and while there are existing technologies for water purification, this is a new use case. This use case that we look at for water purification couples with the electrolyzer in sometimes remote locations. It has very tough physical boundary conditions the technology has to be able to cope with. One thing is intermittency. Start-stop and behavior of the energy, unexpected. This is something the technology needs to be able to handle. The second thing is serviceability. So we need in remote location a technology that is very robust and needs low maintenance. Question is, can the water purifier guarantee that? And the third thing is sustainability. So green hydrogen approach must also assure that in the water purification there's no harm to the nature, and we don't take away water from other uses. So those 3 points are important for a water purification device, and at Bosch we made up our minds what can be a good technology, and we are entering into the market with a solution I'm showing here on the screen. This solution is containerized, and it combines a mechanical vapor compression distillation with an electrodeionization unit. You can imagine this is a container. You input water, this can be seawater, you get out ultra-pure water to process for the electrolyzer, be it PEM, be it alkaline or other electrolysis technologies. We have sized this water purifier to supply the process water for electrolysis up to 15 megawatts of capacity. And it weighs about 10 tons. It takes in seawater of 50,000 microsiemens per centimeter, and the output is ultra-pure. One thing that you may wonder if you hear distillation is evaporation and condensation. That takes a lot of energy. However, we have implemented in our device recuperation of this latent heat needed for evaporation, and this results in the fact that we need a very small fraction of the energy of the entire system coupled with the electrolyzer. To produce a kilogram of hydrogen, an electrolyzer needs around about 50-60 kilowatt hours. The water purification coupled to that electrolyzer needs only up to 0.2 kilowatt hours. This means we have really marginal amount of energy that is needed here for the water purification. And rather than trying to save any energy there, we advise to focus for water purification on its robustness, so that you make sure you have no downtime ever of your electrolysis system due to any failure that you might have in the water purification. We want to point out some features of water purification technology for hydrogen production that we consider are the most important ones. The one is that has to do with the intermittency of renewable energies. It must be dynamic. So any changes in the load, the device must be able to follow within seconds or up to a minute. The second thing is it must be robust. Some of our customers are asking to apply the device in desert areas with strong winds or outside in the offshore area. We have to make sure that it has always the constant ultra-pure water quality, and it has very low maintenance. And we aim at once per year to plan a maintenance, so in order to avoid any operation costs. And the third thing is sustainability. So when you have water purification, you always have an output of the ultra-pure water, and you have the brine, which needs to be disposed. And we can minimize this brine disposal with our technology. This is linked to the fact that it's a distillation technology, and we can dial up the water efficiency up to nearly 100%. And the second thing is that related to sustainability, we don't want to add any chemicals to the process. If you look at this one example, and this is a very innovative, exciting example, and you know it, the decentralized offshore hydrogen production, it becomes immediately clear that here, where you turn seawater outside on the ocean into ultra-pure water to be processed by an electrolyzer right there at the wind turbine, you do not want to add any chemical to the process. A state-of-the-art, membrane-based water purification device does need lots of chemicals. We want to make sure by adding no chemicals, this is a sustainable approach. I mean, with green hydrogen, we're all here because we want to be able in some decades to turn to our grandchildren and say, back in the 20s, we turned this climate change thing around and we introduced green hydrogen, but we don't want our grandchildren to come back to us and ask them, why didn't you care about the quality of the water? So no chemicals to be processed here, maximally robust and low maintenance in order to be able to have a maximum uptime with this green hydrogen production scenario. So let me point out what we do at Bosch Manufacturing Solutions. What I just presented is a water purification device that we are entering the market with. We also have at Bosch Manufacturing Solutions the integration of electrolysis systems for specialized applications, including H2 testing. We also have production equipment and testing solutions for hydrogen injection components. We have them for fuel cells, for the mobility sector, and also for the stationary energy sector. I welcome you to join us in our booth number 1. My colleagues and myself will be happy to talk to you about those fields. Thank you very much. Looking forward to questions.
Here they come. Thank you, Wolfgang. One of the questions is what happens to the residues of the purification process? So, for example, the brine.
Right. So, of course, when you have input water, and be it in that example, it's seawater that I just showed, you have the ultra-pure water, but then you have a concentrate of the salts, and you have to dispose of it. What's important there is to comply with regulations. Yeah, right? And the regulations, they may forbid that you add any chemicals that you need for the process into the environment. And so it's always an advantage to be able to say that in the process there are no added chemicals. Mm-hmm. What really happens then in practice is you dilute this concentrate again and then dispose it off in the environment.
Into the sea.
Right. In this example and in other examples into the sewage system.
Okay. How much water is lost during your process?
Right. Yeah, that very much depends, you must say. So in this setup that we have now, we have a 50% water efficiency, but that's really by choice. We can concentrate up the water quite high, and if needed, we can actually concentrated up to nearly 100%. There's technologies we could add to this. This is the so-called zero liquid discharge, which is an innovative technology we could add to it technically. But this is possible. But right now, at the moment, we have 50-50. So you give me 2 liters, 1 liter is for the electrolyzer, and 1 is disposed of.
Okay, good. Is it also possible to use the water purification system to make drinkable fresh water out of salt water?
Generally, yes. Yeah. So the distillate water that we produce, it can be remineralized and then be consumed as drinking water. And there are ways to do this. And I would consider this really as a chance, as a dual use case to produce water for green hydrogen production, but also for the people that work right there. I mean, we're looking at producing hydrogen in areas which are water scarce, and this is a possible dual use case.
Okay, yeah, very good. Could you elaborate again on how the energy required for the distillation is very low? You said normally you would need a lot of energy, and then could you make your point again why it is low in your...
Okay. Yeah, so the distillation of energy, of water, is usually energy intensive. What we do is we evaporate water that needs lots of energy. We have then a steam compressor that raises the pressure on a higher level. This also means that the condensation that then happens is on an elevated temperature. And that means condensation happens at a hotter temperature than the evaporation. Then you can use heat exchange principles to win back that energy. That's the recuperation I mentioned. And this ends up in the end to be an energy efficient water purification method. We must say it's more energy consuming than a cold membrane-based technology, but like I mentioned before, we are still in a range that the energy consumption for water purification is tiny compared to the electrolyzer.
The time is out, running out. There is one question. I mean, this is a mega question. You see, would you like to make any short, specific comment on that, and then ask maybe the person who has asked that question to join you tonight to get into a longer discussion? Is there any particular point you would like to highlight on the question, how you let's say, with your applications also intend to stay competitive versus other competitors, for example, Chinese competitors here?
So we believe we will have with this technology especially for the use cases in remote locations, a competitive, good solution with a good product market fit. That doesn't matter if we're in China or Europe or anywhere. So we're going worldwide. And yes, I follow your recommendation. Please, let's continue this discussion in the booth.
Great. Thank you very much, Wolfgang.
Thank you.
Coming to our third presentation, I'd like to welcome to stage Christian Tewes, the Vice President, Commercial Vehicles and Engines at Witzenmann GmbH.
Thank you.
And he advises basically to avoid the Big Bang and to ensure H2 safety with flexible elements.
Thank you very
Here
much.
you go.
Thanks for the welcome. Thanks for being here and presenting us here in front of all of you. Great to have that session. It's needless to say that on such a conference which we are attending, we all, besides all the strategic discussions, fancy approaches and global strategies, we all have to think about one thing, that's safety. And whatever installation we want to realize in the production or transportation of H2, it's always about one thing. We want to avoid the Big Bang. In the next 10 minutes, I'd like to take you with me to some level of detail that may be very often underestimated when we talk about hydrogen realization and global strategies. At the end, a media has to be transferred from A to B safely. Welcome to the world of pipes and spools and hoses. Welcome to the world of Witzenmann. I think that if you're not coming from the southwest of Germany, close to the area of Stuttgart or Pforzheim, you may not know us. But I also think that very many of you who are still driving combustion engine cars drive parts and products from us around. Witzenmann is a typical hidden champion, existing since about 170 years, coming from the manufacturing of jewelry and grew into the industry with the production of metal pipes and metal hoses, and then developed further with OEM, engine builders and car manufacturers into the world market to be a global player. Right now, Witzenmann is active in 17 countries with setups, employing 4,400 people, and yeah, as I said, being a global player and also in our areas which we are now discussing here. We are also supporting the industry now in the transformation towards alternative concepts in fuel and energy. And as I said again, it's about transmission of gases and liquid media. As we are supported in 4 different branches, we are actually active in 4 different branches, we can gain our experiences from all these different branches into our business. Actually, they all require totally different elements. For example, the mobility, which contains passenger and commercial vehicles, requires, of course, scale-up ability. So we need to scale up our production. We're talking about numbers of parts that we produce of 800,000, 1 million per year. Other side, the aerospace industry requires very high demand in terms of technical cleanliness. And that shows that we already have, in this whole time frame of experience which we gained, these different requirements always on our table. And always safety is a part of it. Just to give you also an example where products from us are installed. So you see us in the electrolysis area with pipes and expansion joints. Realizing this also in the storage of hydrogen. We have expansion joints in liquefaction plants. In the distribution, we also see valve bellows that we produce and LH2 transmission lines. And finally, also in the utilization, whether it may be fuel cell or hydrogen engine, you also have our connection pipes and any kind of flexible elements in this established. So we are actually already active in several fields of products. However, in the H2 world, the safety requirements from customers are very high. Very often, due to missing guidance, regulations, and norms, the customer requirements are even higher than they should be. So they're over-engineered. Just to be on the safe side, everybody wants to cover, let's say, the situation that he doesn't really know, what is the risk that he has to cover. However, as coming also from different other areas in the aerospace business, we are used to take the customer where he is with his questions in the engineering, in the development phase. So we elaborate on his demand to make sure that we don't over-engineer the safety requirements. For example, we have the experience in the CERN Institute or in the Ariane rockets or the Orion rockets or the ITER. Everybody knows what can happen. And this is also what we try in our labs and our test benches, that we blow up our own products to see what can be compensated in this part. How can we deal with that? And in terms of safety, we try to avoid this. We try to avoid that out of this the Big Bang may happen. Now, how do we do that? So, of course, firstly, we follow the general regulations of quality standards which are there in the industry. We are also preparing ourselves to develop more, to be ready for the next step of development, because quality aspects and norms will come with the regulations. As well, we have a very high level of expertise in welding for flexible and non-flexible pipes. Also, we control it. We have a centralized concept to measure the welding seam with X-ray. But also, we go into the field of developing monitoring systems on our products, on our flexible products, with sensoric. At the end, of course, we have a target to make leakage detection. Two elements are very important for us, and as also we see them as a very clear element for the security and the safety is, of course, the testing, because this is experience, and it's about the technical cleanliness. Testing, you see several examples of testing that we have to do. X-ray testing is one key element for making sure that we have the right product in the market. The hydrogen embrittlement, we overcome with the choose of the right material. We establish and proceed that the H2 readiness is actually living in each and every step of the engineering. And of course, it's again, testing, testing, testing. Low frequency testing, vibration and pressure cycle testing. So we test whatever we can to see how far we can go. Also, in the field of technical cleanliness, the H2 world requires a lot. And here we decided that technical cleanliness we make as a core element in our, let's say, living character, having this as a central department, interacting with all the other departments, making it a clear element in the production and logistic lines. So that means we make sure that for the production area, we also come from aerospace requirements, using pressure chambers or clean rooms. And then also in the production line, we use several elements, several material to clean substances, to clean the products, and make sure that we monitor the whole process in the production line, so we can really ensure a technical cleanliness throughout the whole engineering and production process. It is very cost intensive. It requires a lot of, let's say, monitoring, but at the end it pays off because it's a matter of safety. As a company, of course, we do what we do here, networking. We also exchange with institutions and associations. We want to be part of the development. We want to be part of the club. We enjoy to also give our experiences into the market. And therefore, we are also here. So we really enjoy to exchange with you, to exchange with shareholders, with customers, with collaboration aspects, because the whole development that is in the H2 market can only be done together. And time is of the essence. So now you see that the development and production of these little tiny pipes and, let's say, tiny little things that are used in the hydrolyzing world, they are not trivial, not in the H2 world. There's a lot of engineering and efforts in it. I hope I could give you a different perspective to change from a global strategy aspect to a little tiny aspect. And of course, from Witzenmann, we are happy to welcome you on our booth 34, right? Just opposite side of the entrance, and discuss further questions, ideas in the H2 world for the next steps. Thank you for your attention.
Thank you very much, Christian. We still see the H2 chain from electricity generation over to the end customer. Where would you say do you focus, or will you focus as a company, or where do you see kind of the biggest dynamics going on at the moment? Where are you involved? Can you give us some insight about kind of your view of the hydrogen industry and value chain?
As you could see, involved, actually, we are on each and every step of the chain, depending on, of course, the scope. I mean, we see that I'm representing also the commercial vehicle part of our branch, that in the commercial vehicle area, the use of hydrogen will be coming in the future. It's not the right time right now. Of course, we still have, and we're talking about development, we have to be part of it right now. I see a big aspect of focus for our interest business is in the hydrolyzers. And I think this is also some element where we can all learn a lot, because everybody is pioneering somewhere here and there. And this is, I think, one focus area that we are going for.
Okay, good. Thank you very much. As a parts supplier, where are you supplying a part of an overall system? How do you work with your partners to ensure that the whole system is safe? For example, in your product, that is in development for 700 bar HRS applications.
Yeah,
how's
yeah.
the
700 bar is
partnership
one element that is also something which we are working on. In general, the partners and also our vendors, when we're talking about material or subcomponent vendors and so on, are part of our quality chain. So whatever we do, as I mentioned, especially on the technical cleanliness aspect, we integrate this into our chain of quality aspects, and that is of course something which we do on each and every workstation basically. And as I said, we also have a monitoring system, so we have to make sure if the part goes of different workstations that the technical cleanliness, for example, is being followed on each and every step. On the 700 bar topic, this is a special thing. There we are in development. I don't want to give too many details about it, but at the end, of course, safety, as I said, is a clear topic. We require this from our vendors. We work in this field with our collaboration partners. We also search for collaborations in the market. And this is basically it.
Okay, well, are you willing to answer the last question quickly again? Especially converted H2 pipelines are often criticized by the public due to safety concerns. Which experience did you make in this regard? Converted pipelines.
This is actually the reason for the title of the speech, is avoiding the Big Bang, because this is always a sort of Damocles which is over everybody. I think we can only overcome this with experience, with what I said, also testing. We have to come to certain algorithms out of our experiences in the part testing, because what I said is the market and let's say the feeling has an effect on the market. The safety aspect is always a big issue, and it makes also the requirements from the OEMs, from the system integrators, always high standard. At the end, if you follow all these standards, it's great. We want to follow that, but it's unpayable anymore. So we have to find a decent compromise, because it's still safe that we can interact. But this is what I say also. We have to develop this together. It cannot be done just by the part vendor. It is always stepping out of this box and going together with the other suppliers.
Right. Thanks a lot, Chris.
Thank you so much. Thanks.
Coming to our fourth presentation, and this is given by the Senior Vice President for Hydrogen and Sustainable Technologies of the company Johnson Matthey, and it's Dr. Eugene McKenna, and he will introduce JM's ammonia cracking technology to you.
Thank you very much. Thank you. Realizing I'm getting close to being between you and beer, so I'm impressed with the number of people who are still here. It's great to be here, great to get the invitation to speak here. I always like to come to Berlin. I tell my colleagues that it's the best food and beer that you get anywhere in the world, but so far I'm the only one who believes it, so I'm here. It's also good to get a chance to talk about ammonia, because it's often cited as part of the solution that there will be to moving large quantities of energy and chemical feedstock around the world in a net zero energy system. And it gets kicked around, but getting quite specific about what we need to do, and also the fact that we need to crack it back to hydrogen for it to be useful, is sometimes a little bit glossed over. So first of all, I'll tell you a little bit about Johnson Matthey. We're an old company, more than 200 years old. We had our birthday celebrations a few years ago. And we survived that 200 years, starting with expertise in platinum group metals, by continually adapting to market needs and to our customers' needs. So we're not doing the same thing today that we did 200 years ago, and a lot of it based on science and technology. We've been involved in hydrogen right from the start. So Mr. Johnson was friends with Michael Faraday and provided him with platinum to take his first steps in electrochemistry. And also with William Grove, who invented the first fuel cell more than 150 years ago. So it's a technology that has been a while in getting to arrive with its time, you could say, and we've been part of the journey all along. We're still market leaders or heavy participants in the hydrogen economy, so our catalysts make one of the largest contributions to the hydrogen that's produced today. And we're also we're heavily involved in PEM technology, providing the components for PEM fuel cells and PEM electrolyzers. And more towards the topic I'm talking about today, we're a catalyst and process technology company that makes a variety of processes that we license in the low-carbon economy, such as making sustainable aviation fuel or e-methanol or e-ammonia, to give a few examples. And cracking ammonia, making ammonia cleanly and cracking it cleanly are part of that group. So why is ammonia cracking important here? Well, if we look at the world energy system that we have today, we move an awful lot of energy around the world. And looking at the way the LNG markets have evolved with the issues that we have in Europe at the moment, you can see the amount of energy that needs to move around the world in a carbon economy. Well, the same is going to have to happen in a net zero economy. Unfortunately, the sun currently shines and the wind currently blows, sometimes in far-off places from where markets currently are. It's difficult to move electrons. Hydrogen is a wonderful thing as a chemical feedstock and as a high-density source of energy, so that'll be good. But moving it at close to absolute zero is a new technology. It can be done. It'll be expensive in terms of energy and cash to move liquid hydrogen over long distances. One solution is to convert that hydrogen into ammonia, which you can move about at much lower or much higher temperatures and lower pressures. And that has the advantage that it's a known technology. There's over 20 million tons of ammonia that's moved by ship around the world today. So there are known technologies, shipping companies, people know how to handle it. There are known qualities of ammonia that we know what people know what they're dealing with. So what are the use cases? So imagine ammonia produced, hydrogen produced in Australia turned into ammonia, moves around the world to Europe on a barge, arrives at shore. Well, it could be cracked in decentralized locations into hydrogen and nitrogen that go straight into a gas turbine. There are other delocalized applications like producing hydrogen for fuel cell applications, but a really major use case will be centralized cracking near to ports, near to shore, to put high quality hydrogen directly into grids. And that's the use case that I really want to talk about today. So one thing I should say about Johnson Matthey's process technology business is that quite unusually, we're both a process technology business that's heavy on engineering and modeling, and we're also a chemical company that makes catalysts. And that catalyst technology put together with an understanding of process technology that where we design and license processes enables us to work on both of those together and to iterate systems so that we get the best catalyst for the best engineering solution. This is very useful for producing systems that are optimum in efficiency and also optimum in CapEx. So low CapEx, high efficiency, low OpEx is going to be really essential in this world, particularly in power generation where, for example, margins can be wafer thin. It was interesting listening to the companies talking about startup technologies earlier in the day. We were looking back at our heritage in ammonia cracking. And the first patents that we could find were back in 1931. Ironically, the use case there was to produce nitrogen. We threw away the hydrogen. People wanted the nitrogen at the time, couldn't think of a use for hydrogen. In the 1950s and 60s, we developed the world's first nickel catalyst that replaced iron catalysts that were being used at the time, ironically for heavy water applications at the time. And that nickel is really robust for high temperature and longevity. We have some historical experience as well of actually making small ammonia crackers. And some of those are still for sale today from people who bought the technology off us. And we also have operated ammonia crackers in plant startups for other technologies where it's been useful to have hydrogen for reduction or nitrogen to make sure there was a blanket of inert atmosphere when starting up other types of plants. We also have technology for purifying hydrogen. It's a membrane technology with palladium, which can be quite important as well. Recent developments include developing low-temperature PGM catalysts, which we have put into Australia's CSIRO's delocalized low-temperature ammonia fueling systems. And finally, we've developed a commercialized flow sheet for cracking ammonia at a world scale. So I thought, having listened to the previous presenters, that it was time that we put some chemical reactions on the board. I thought I'd either lose There'd either be a cheer or everybody'd walk out at this stage, but it's kind of somewhere in the middle. So two reaction schemes up here. One is steam methane reforming, which is where most hydrogen is produced today, and the other is ammonia cracking. The interesting thing about them is that the enthalpy change is very similar for the two. They're both endothermic, and the temperatures and pressures at which the reactions happen are also very close. So basically, if you're good at steam methane reforming, you should be able to work out how to do ammonia cracking. And we have a long experience in steam methane reforming. It's all about managing heat transfer and making sure that works and things don't overheat and you get heat transfer and mixing during a reaction. But the large-scale ammonia crackers that we see will look very like steam methane reformers. So here's the actual flow sheet that we've developed in Johnson Matthey and is now commercialized. And over to this side, it looks very like the technology for other known technologies today, like those for making nitric acid or for making cyanide, and that's a vaporization of ammonia or the pressurization of ammonia. Then we have the cracking in the middle, tubes, high temperature, top fired, which looks very like steam methane reforming. I'll come back to the idiosyncrasies of our process. And on the far right, all of that cleanup and heat transfer is very much like making methanol or making ammonia at world scale today. What we've chosen to do in the center is to fire this cracker with ammonia and also with some waste gases from the process streams. Other systems will fire that with natural gas. So our method is a truly net zero solution because the fuel for firing the cracking is also a net zero product. We've done a lot of work on the quality of the feedstock, and that means we're ready to go directly to a commercial system. I think I shall go a little bit past that. What's enabled us to go directly to a commercial system is our experience in heat transfer. So the world's largest hydrogen production facility at the moment, which is 800 tubes, 500 megawatts of capacity in Trinidad, is a Johnson Matthey design. We've also got great modeling, which enables us to go from using that expertise to go from a theory and a model directly to a world-scale product without lots of pilot stages in between. We're world leaders in the emission controls coming out of these processes, and we've got a range of catalysts now for tailored applications. This is what a tube looks like. We've put our Catalco 27 nickel catalyst on this quadrilobe pellet, and we have kind of world-scale manufacturing facilities for this catalyst. The way the pellet stacks in the tube enables great heat flow and gas flow through the reaction tube, which is very important. I've got here a list of processes that we've developed over the years in conjunction with major chemical industry partners. And what they do is they've invented a technology in the lab, and they've come to us to help commercialize it and to scale it up because of our expertise in taking small laboratory-scale processes to world scale. And these are some of the examples. And you can also see we've got partners who've come back time after time because of our success in commercializing these experiences. On the right, this is a 600-ton reaction vessel for methanol conversion, and that's a 200,000 times scale up, and it went directly from a model on a computer all of the way to a reaction vessel without any intermediate pilot stages. So, to finish, ammonia cracking is, we think, going to be an essential part of the ecosystem in which we have a net zero energy system in the world in the future. Ammonia will be important. Being able to crack it will be important. What we hope to bring to the party is a technology that is robust, ready to commercialize right now at today's levels of efficiency. So it doesn't have to go down a curve of improvement. It's available at full efficiency today, based on our long expertise, and we've already got the catalyst expertise to make that happen. In terms of progress, we've got a pipeline of customers and projects at the moment looking to start up their plants in 2027, and we continue to partner with customers for example, we have an example of us working with Doosan on a process to crack ammonia and go directly into their combined heat and power units. So I think I'll finish there. Thank you for listening at this late hour of the day. It's been great to see the energy around this today. I'm looking forward to some of the sessions tomorrow looking at the resilience of hydrogen supply chains and how to import green hydrogen. Thank you.
Super. Thank you, Eugene. And again, we see here some examples of partnerships.
You do indeed.
And maybe customers. What kind of customer segments do you foresee to be very important for the ammonia?
So I think it's interesting because we're very familiar with customers who make ammonia as we are a major supplier of technology into ammonia manufacturers. New people will crack ammonia into hydrogen. So power generators, potentially, people who run grids, people who run power plants will all be, and there's a space as well, I think, for new players in this space. But I think the large integrated oil companies are potential future operators of this technology.
Okay, good, thank you. Now we've got questions here on the list. What is the status of your reverse water gas shift technology? Which technological readiness level do you consider?
Well, it's already fully commercialized, and it's already, for example, the first commercial plant is being constructed at the moment in the Basque Country in Spain with Repsol and Aramco. So that's one that's ready to go, and once again, there's quite a few people interested in that technology. So that's just what you need: clean hydrogen and clean carbon dioxide, and you've got any hydrocarbon you want.
Okay, very good. How is the proportion of JM working on the catalyst development nowadays?
So JM has a number of businesses. So we have our old Clean Air business that makes automotive catalytic converters, and then very much a focus on catalyst technologies, which is what I've just been describing, our catalyst business and our process technology business. The third leg is hydrogen technologies, which is that PEM technology. So those are the three legs, all supported by platinum group metals. So several thousand people and lots of scientists involved still working in that.
Okay, great. Thank you very much. Right on time. And yes, if everybody would like to have further questions, obviously you will meet Eugene at the beer party tonight, as you said, right? Good. Thank you. And I'd like to ask two gentlemen on stage, Dr. Stefan Kneip, Partner and Vice President New Energy Technologies, and Peter Michael Holzapfel, Senior Consultant Hydrogen Markets, both from Siemens, and they will present on the native digital green hydrogen plant, advisory solutions and implementation. Looking forward to your presentation and the short discussion afterwards.
Thank you so much for the introduction. It's just about time to leave for the drinks networking, but it's also just about time to mention digitalization. I was earlier looking at the word cloud. Some of you might have seen it in the previous session on what is on your mind when you think about realizing projects, and there was LCOE or LCOH, and there were lots of other KPIs, sustainability, etc. And there was one word I think that was missing, and that was digitalization. And as it can also be an enabler in making these projects work. So we are here today to talk to you about the native digital green hydrogen plant and how we can use the means of digitalization to take you through advisory solutions into implementing some of these projects. And I believe there is a way to advance the slides. The green button, if that works. So now, hydrogen economy is a pretty complex thing. If we're looking at this, we are finding many of the talks that we've had over the course of the day on this picture. At the very center of it, obviously, if we're talking about green hydrogen, there is the electrolysis and there is the green hydrogen plant. There is a lot of other things. We just spoke about the purified water that has to come somewhere where the electric energy and the green energy comes from. But then there are also the downstream refinements and the uses of hydrogen, the ammonia, the cracking and all of that, the transport. So this is a pretty complex system, at the heart of which is the green hydrogen plant. And that is also, let's say, a system that has a complexity that really needs to be managed. And some of the questions, if we think at this center of which is the green hydrogen plant, some of the questions that we encounter from our customers and from partners are, for example, how do you make such a first-of-a-kind facility? How do you really, where you don't have a blueprint that you can easily copy across, how do you really make that work? How do you How do you manage, for example, the intermittency of renewable energies? How do you, for example, also maximize the revenue from different offtakes that you can have in your project? And then we're looking at, let's say, balancing the trade-off, so to speak, between, on the one hand, you have, let's say, managing the risk of jumping into premature maybe technologies, but then also the advantage or the benefits of being the first mover in the market. So some of these questions that we accompany you through along your journey, and you can get this enabled through digital technologies. And I'm going to hand it over to Peter in a moment, who is going to run us through that typical journey along which we're enabling you on realizing some of these projects.
Thank you. Well, thank you for your attendance here. However, what I would like to emphasize with this slide is that we're actually the enablers of plants. We're not the EPC. We are not the manufacturer of an electrolyzer as Siemens AG. Most of you are probably aware that Siemens and Siemens Energy have been split entities for approximately 3 or 4 years now. So what we do in our daily business, and we've been doing this for quite a long time now, the first part of X plant I dealt with was 13 years ago. We supply equipment to plan, optimize, and operate a power-to-X plant or a hydrogen plant. And in this process, we're dealing with multiple stakeholders that are involved in the project. So it's not that we have one customer, we're actually talking to multiple customers, because all of them have the need to somehow optimize and digitalize their equipment, and everything has to come together. So we start off in a very early stage with in these projects talking to the investors. So we're actually often even involved in the investment phase. And then you go through different phases of the project. You have a conceptual design, and in this design phase, you might need software to build up a digital twin of the plant, which we strongly recommend because it just helps to reduce faults, ramp up the project by a magnitude, basically, get it running a lot faster and more safely and securely. It will then have a process engineer phase, and so on and so forth, as you can read in here, and you'll have the construction phase, and at the end, right at the end, you'll have the operation. So what we really deliver is a platform, a technological platform to reduce the interfaces throughout this process, and to ensure that the projects are realized in a very lean and fast way. And our customers are typically the EPCs. There are engineering companies. They're the package unit suppliers. So an electrolyzer manufacturer, from our perspective, is one of the major package unit suppliers. But for example, we just heard that it is also about, for example, water purification. That's a package unit that has to be optimized and integrated into the entire plant, for example. And what we deliver is, we also learned in the presentation previous to mine or to ours, that, for example, you need a software to upscale very quickly. And we deliver that software in terms of planning software and digitalization, meaning to build a digital twin that you can then, in the operation phase, attach to the slide. So I've got a bit of a different view coming up on this. Basically, to show what we do, we have remote and automation process control. That's typically where we come from. We have process control systems and automation systems, S7 or PCS7 based, depending on the size of the units. That's what we typically are known for, which allow you to have also a remote operation. It's all about environmental health and safety within these plants, because we have to ensure that the plants are operated in a safe way. We deliver digital twins. As I said, digital twins, it's more than just simulating the plant. It's also integrating that simulation into the running plant so that you get a learning loop, that you learn from the operation, that your model learns from the real data of the plant, so that you can optimize the plant while running it. and go through different scenarios. It's about cybersecurity. We have an entire portfolio of hardware and software regarding switches, routers, firewalls, industrial grade, to ensure that you won't be hacked. It's about virtual commissioning. That would be a topic, for example, that you have a training software for your operation personnel, that you have a simulation set up for your training personnel, for your operating personnel, that you can enable them to run this plant without working on the actual running plant, for example. It's about predictive maintenance, meaning that you see when your equipment needs to go into some sort of service. For example, the electrolyzer, that you know when to sort of take a stack out of operation, do the work on it, and then put it back into operation. I won't stress the simulation, I've done that already, and it's about asset monitoring, meaning that you know what kind of assets are in your plant, what basically is out there, and that is basically what we deal with in general. So we deliver like a data hub. The data hub meaning we have the platform that when it gives you all the data available for your plant. That's what we have as software. Enable your workforce basically by simulation training. That's what I was saying. If you have like a simulation of your automation environment, so you can train your personnel for the operation. We have software for the design and engineering, basically, as a digital twin, so you can set up the plant from actually 3 different angles. It would be the actual plant you can simulate, but you can also simulate the process, the chemical reactions within the process, what's happening, and that is what would enable you to scale up very quickly. It's about security, I already mentioned that. It's about integrating the OEM packages, which we call package units, compressors, electrolyzers, water purification, to name some of them, for example, and to ensure that they're integrated into an overall concept from the automation. We're quite common, or very, very common, within the package unit suppliers. So that makes it easier to set up an entire plant with a platform. It's about the business management, giving the management of the plant an insight of what's happening, giving them key performance indicators so that they know very quickly what's happening in the plant. And it's also about the operation and the optimization, meaning that you can do, for example, a remote operation of the plant, remote maintenance, which are 2 different things. So that's basically what we do. To give an outlook of what this could look like in the future, could go a lot further even. We could even be talking about integrating drones, for example, for further development of the plant, to integrate their pictures and into a digital model of the plant. So you can have a 3D mock-up of the plant. We can do this currently already. Also the drone pictures we can integrate, so you can set up basically for training purposes, but also for service purposes. So you can have a 3D model of the entire plant that you can go through with an augmented reality. So you give your operation or your operator a tablet, and he's capable of taking his order and going through the plant with the 3D mock-up to then do a service job at the equipment that he is guided to with the entire documentation that is also provided, just as an example. So it's about data transparency in this case, for example. It's about rapid data-based decision-making, maybe even automized decision-making at the time. It's of course about environment, health and safety. It always has been in the process industry, so that is an old requirement. That's nothing new really. It's about cybersecurity, becoming more and more crucial. It's about intelligent and predictive operation of the plant, meaning that you know what might be happening, that you can react in terms of scenarios. It's about flexible and modular design, so that you can basically enhance your operation or build it bigger. And it's about a secure workforce and enablement, meaning that you have the possibility to train your workforce on these tools. That's generally just to give you an overview in terms of what we do in the digital sphere. There's a lot more to be said. We do measuring equipment, so we also do hardware, not only software, gas analytics, rectifiers, but that is the digital sphere. In the core, there's always the automation, but there's a lot more to it.
So mindful of the time, let me just take you home. I think many things might also start without even having already the groundbreaking and an actual project. So along these first steps, our value proposition also includes advisory services that might just include such questions on where do you get the electricity from, how do you create a positive business case, how do you get FID, how do you even get an investor story put together. So these are some of the rather more advisory questions that might come before actual technology is of use. And this advisory is really building on the deep domain knowledge and the tech stack that Peter was just introducing to you. Many colleagues and a strong team, happy to engage with you also further over drinks. And thanks so much. Thanks for your time.
Yes, thank you. Thank you, Stefan. And Peter, would you move one further? Thanks a lot. There is a question on the digital services or on the IT services that you provide, and it is what process control SIL level can you guarantee? Can you?
Well, anyone you want, basically.
Okay.
Depends on the requirements of the customer. Yeah.
Mm-hmm. So everything possible there.
Yeah.
And also build on lots of process plants and lots of factories and large-scale installations that are already in the field across the world. So I think there's really the safety and security is very important.
Okay. One thing I was asking myself is to implement some of your solutions also. How is the integration working with customer processes or customer systems? Are there any requirements to that? How do you manage interfaces there possibly? How would you comment on that?
A couple of thoughts come to my mind, and Peter, you can add.
Exactly.
I mean, definitely the one of the opportunities that the green hydrogen plant also brings, that it is by and large a greenfield approach that you can take, and therefore you can really also load it with all the technologies and think about very consciously, not always struggling with the brownfield side of things. But partners in our ecosystem are very important for us, and we also have that closely linked together through our accelerator, which you might have heard of. So basically, working together with your setup and also with your partners, for example, is everyday habit of us. Yeah.
Mm-hmm. Anything to add?
No, basically, I mean, you can actually couple any kind of interface, but it makes it easier, of course, if you have a platform that is homogeneous. Yeah, it just makes it easier.
Okay. Final question for tonight, maybe on the advisory side. You presented that what from your perspective, let's say, are the 3 hottest topics that also people should be aware of in the room that you are currently consulting on or doing research on and see?
We heard it a little bit also in the previous talk from Johnson Matthey. I think the whole transport and the logistics side of hydrogen is somewhat a missing puzzle piece. There's been a lot of effort on the production and there's been a lot of effort on the consumption side, but it's great that also that gap is being consciously looked at and being closed. I think that is definitely one element that is very important. I think then we're having a big regional variety. There is an ecosystem that is in Europe, but then we're also having rather much more different questions and constellations in the Middle East or elsewhere where there are mega and giga projects. So really, this is not a one-size-fits-all. I think that is really quite different depending on which part of the ecosystem are you looking at. And last but not least, it's a great opportunity, and it's also good that we have maybe come a little bit past the hype curve now into a level of a foundation where there is a lot of reality. We're not trying to solve every problem with hydrogen, but the problems that really are meaningful to be solved with hydrogen.
It's hard to get to groundwork now.
Well, I believe the topic that we are trying to address more is don't underestimate the potential and the use of a decent simulation. Because I believe, talking from practical experience, as I said, I've not been doing this for 2 days, I've been doing it for 13 years. I've seen the problems that customers have run into by just quick and dirty trying to build a plant. It's not the right approach to take if you're talking about a bigger plant.
Thanks a lot to the two of you.
Thank you so much. Thank you.
maybe you just wait here, because I would just say thank you also to everybody in the audience for asking a lot of questions, listening to us. And now you have deserved, I would say, a glass of wine, a glass of beer. So please join us now for the reception. I think it starts at 6, but we can assemble before. Have a nice evening, and then be back fresh in the morning, I would say, tomorrow morning for another interesting day of presentations and discussions. Thank you, and see you. Oh, sorry.
Yes.
Daniel.
Yes.
I guess to hand over to you.
Because I guess we have one more who is now presenting, which is Uwe. He's at the starting block, so to say. So sorry, guys, no drinks yet. One more presentation, but then we will have the drinks. So over to you, Uwe.
Sorry for this one, Uwe. But now the stage is yours. Everybody is really focused now.
Thank you very much. So can you hear me? Yes. So I don't hope that anybody's leaving, because I see you all. That's good. So I think I have another more minute then. Yes, my name is Uwe Kueter. I'm from HQ Systems, and I lost my voice this morning on the Autobahn between Hamburg and Berlin somewhere, so I have to apologize if you don't hear me well. I do my best. I have only 50 minutes, so I think I will make it. The organizer is a little bit worried because I have about 40 slides, but I'm a fast-talking guy. So for me, I think you will see all my slides, and then we can still have a coffee together, and we're still in time. So let's see. But I want you to get like an idea. You don't have to remember all the slides. You get them online anyway. Just relax, lean back, fasten your seatbelts, and then we can go. But before we go, I need your help. I would ask you 3 questions, and maybe you have still the power to raise the hand. I don't know if you make it. Let's check it out. First question is, if you're from a company or institution or somewhere, doesn't matter, or private, who has actually today a running electrolyzer in a company, institution, or at home? Who has a running electrolyzer? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, let's say about 12, okay? Who is planning to have a running electrolyzer who within, I don't know, the next month or so, who ordered an electrolyzer, who's building an electrolyzer now, who will operate an electrolyzer this year? 1, 2, 3, 4, let's say 5, maybe 6. Okay, who will think about having an electrolyzer? Maybe next year or so. Yeah, 3, 4, 5, 6, 7. Okay. So last question: who will never order an electrolyzer because he does not like hydrogen? Good. So I can proceed with my talk. Thank you very much. This short agenda. Where we come from, you see the agenda. I skip this. We are a startup, but we are a spin-off. We are 4 years old. We are a spin-off of a hydraulic company. So family-owned business, 65 people. Technology, everything was there, available. Technicians, know-how was there. So our managing director, in connection with Inapter, became the idea to start the hydrogen, the HQ Systems hydrogen company. We are an assembler. We are a system integrator. We buy all the components and we assemble. Our know-how is how to make a complete system. These are some of our partners. Our main partner is Inapter. You have seen Inapter today on the stage. They are outside, so I don't think I have to explain who Inapter is. And therefore, we are talking here about AEM electrolysis, anion exchange membrane. And I know that you have all learned about it today, advantages, disadvantages. I'm not going to ask you. What I would like to do is because this is a talk about systems, solutions, and use cases. So what I would like to show you is some actual our daily work, some actual projects, and all the components before of a system. So of course, electrolyzers, we offer electrolyzers between 2.4 kilowatt, if you remember, this is the smallest system from Inapter, and 1 megawatt, this is the largest system from Inapter. And in between, we have several systems. So we can provide electrolysis systems between 2.4 and 1 megawatt. That means 1 kilogram a day, between 1 kilogram a day and 450 kilogram a day. And to a complete system, also sometimes you need fuel cells. Here, these are small fuel cells, and larger systems, of course, and you will have larger systems. This probably has the same idea than me. This is the thing I'm not very happy about. This is, in my opinion, still the bottleneck, the storage of hydrogen. So we recommend to store directly at the output pressure of the electrolyzer 35 bar in a 35 bar tank or in gas bottles. This is the cheapest and efficient way to store hydrogen, and the companies usually have space. If you don't have the space, of course, then you need to compress. But here's first what we can offer. For example, a 1 cubic meter tank, you can see here 2.8 kilogram has about 92 kilowatt energy. So the largest tank we can offer is 115 cubic meter big, and it has about 325 kilogram. So if you remember, the Nexus 1000 makes 450 kilogram a day. So this is one tank. Bottleneck. So if you don't have the space, you can use you need to use a compressor. Also, if you need high pressure power for mobile application, I'm sure many of my colleagues have talked already about this. Other components in a complete system are the water purification, very important. Here's a small one, but we also work with other companies providing larger systems depending on the size of the system. Gas dryer, of course, if you need 5.0, hydrogen quality. A battery is always part of a stationary system. I don't know if everybody's aware of this. If you have a battery system, I mean, if you're a stationary system, you will see in my slides, I will come back to that, because the fuel cell is nothing else than a battery charger. Okay, so this is the advantages of AEM. These are modular systems, and so the customer can choose of the system, and he can have small or larger systems. So let's switch to the solutions. We have sold about, I think now it's probably more than 300 cabinets in 40 different countries. And before I start with the use cases, the first market is always education market. Everybody knows this, so universities, technical schools, learning centers, or also the first market is always like backup system. Okay, let's start with with other use cases. First use case we are working with right now, we have customers, is companies, most of them are small and medium-sized companies. They want to replace hydrogen bottles they got from other companies, they pay for it, and want to have their own hydrogen. What they need is like an energy source, usually it's a PV, because most of the companies have their own PV plant on the roof. And all what they need is like a water purification, electrolyzer, and some kind of storage. That's it. And then they are able to make their own hydrogen for their own use. Use case 2, this is an example. For example, like a fuel cell company or all different kinds of companies working already with hydrogen components, and then they want to have their own hydrogen for testing. Second use case is for the heat process. So it's a replacement of natural gas. I mean, we don't have to discuss this. Everybody knows the situation in Germany. So there's a small transition from natural gas to hydrogen. And because most of the companies don't get any more money or not enough money for PV electricity, they think about, they're looking for business case. And they want to have green hydrogen for their own heat processes. So this is how it looks like, this whole system. Third use case is like a biogas plant. The company is producing biogas, and the goal is here, because always the owner of biogas are also most of the time owners of wind parks or PV plants, and they have excess power, and they want always the same. They want to produce their own hydrogen. They need the electrolyzer. They need water purification. They need the storage, and then they want to feed at least 20% into the cogeneration plant of the biogas plant, or part of the biogas plant. So the fourth use case is yeah, I think everybody knows this. It's to increase the degree of independency of autarkic systems. So in most of the companies, as I said, have PV systems on the roof. And so they want to increase their degree. So with PV, it's about 60% usually if you have a good battery and a good optimized system, and they want to increase this degree of independency. And this is how it looks like. And the fuel cell in this system is nothing else than the charging. It charges the battery. So the battery provides electricity to the electrical consumer, and the fuel cell charges the battery. Yeah, this is an example in Poland, use case 5. So my 10 minutes are gone, but I know I have 2 more minutes, and I think that's enough. Use case 5 is, this is the interesting part, because companies, they don't need the hydrogen, but they have excess power of PV, and so they're looking for a new business case, and they would like to produce hydrogen, store it in a trailer, and then sell it. So there will be a group in Germany producing hydrogen, and there will be a group they need hydrogen. So somehow they need to come together. So this will be the interesting part. How do they come together? And this is how it looks like. This is an example. Skip this, you can read this later. So the 6th use case is a project we have in the US. In Germany we have, yeah, it's okay. I think it's okay grid. So the stability of the grid is not too bad. But there are countries they might have problems. And so the project in the US is they use like a bunch of electrolyzer systems. Here we are selling those hydro cabinets as indoor-outdoor systems. And it makes sense to use those cabinets up to 100 kilowatt power consumption, 120 maybe. And then we have a next product. It's called Flex 120. And they use this here, depending on the power, if it's too much electricity or less electricity, they use this as a switchable load and produce hydrogen. This is the project in the US. And the last use case is, I call this a green hydrogen energy carrier. It's like, it's basically the same. What can you do with renewable energy? And here you have the largest system of Inapte, and it's a real project. And so here in this project, everything is being used, or they want to check it out. And so they produce 450 kilogram a day, store it. It's like a small buffer, not a small one, the largest one, but it's a buffer. And this is how it looks like. And this is in reality, it's already at the place, at the site in Braunschweig, and it's going to be operated pretty soon. Thank you very much.
Thank you, Uwe, for using the time very efficiently, running us through all of your use cases. Your broad experience became obvious. And there is the question, which one of these use cases would you say has the highest potential for scalability?
For scalability? Well, if we think about industry, where our focus is on systems around megawatt and less, I know that most of my colleagues, they think big, 100 megawatts, and of course this is industry. So here, our business partners or our customers are small and medium-sized companies, and this is the Deutsche Mittelstand, and so everybody has a PV system almost. I think there's a big potential. So I think everybody.
All of them.
Yeah.
Okay, one last question. From your broad experience and all of that, what do you consider to be the biggest challenge now in
storage?
Next year? Yeah,
it's a storage. Yeah, it's not the cost. Cost is a matter of volume.
Yeah,
and like Inapte came down with the cost anyway, and a fuel cell is affordable. It's a serial production electrolyzer, but storage. There's a 35 bar storage, high pressure, and then of course metal hydride storage. We are working with 3 companies. Yeah, one you may know them from Switzerland, GRZ, and from Australia, of course, and from Hannes from US. So there is some hope. This is like an option in the future, but I think still this is a long way. So we need somebody has to come up with a good idea.
Yeah, so
but I'm been in business quite some years in hydrogen business, and so far I'm still waiting. So.
Yeah, okay, thank you for
You're welcome.
Pointing to that business opportunity and people maybe wanting to developing it together with you a bit further.
Yeah, we have a booth outside, so I will be there during the eating, during the meal. So.
Yes, super. Thank you very much, Uwe.
Thank you.
Sorry again for, first of all,
Thank you.
that rough introduction.
Thank you.